So like I said, this is sort of a tough little question. Let's try to do it. Here we have our two slits, right? And we know we have a central maximum corresponding to theta equals 0, right? What about the next direction? Did everyone get 33.7 degrees if you put in n equals plus 1? So that might correspond, so that's n equals plus 1, right? Is 33 degrees. The next one is out here for n equals minus 1, right? At minus 33.7 degrees. So can we do one for n equals 2? Well, you have sine theta is equal to n lambda over d equals n 500 over 900. So what happens if n equals 2? Then you have 1,000 over 900, right? So it won't work. So how many different directions do satisfy this equation? 3. So let's see what people said. A number of you chose B, 3. That's good. You did better than the 7:30 lecture, let's just say. A lot of them chose just 1. Very good. So the next thing we can talk about is diffraction gratings. And you should think of diffraction gratings as a multi-slit situation. Okay? We can demonstrate that here too. On this little photographic plate, there are very, very finely printed lines which are separated by a certain distance. And once again, if I turn off the lights, you can see a pretty bright pattern of dots on the screen up on the far wall up there. And if I go to a wider pattern, you can see a tighter pattern of dots up there. So there's an inverse between the angles at which you have the maxima and the separation of the maxima. So this is a very fine pattern, spreads out the dots more. That's kind of interesting. Can we see that from our equation? Well, what's the equation that governs the case where you have not just 2 slits, but many, many, many slits? Exactly the same equation. The condition for constructive interference from all the slits is still the same, that d sine theta is equal to n lambda. So the bigger d is, the smaller theta is. The smaller d is, the bigger theta is for a given value of n. That's why when we change the number of slits per millimeter, you see the pattern of dots spread out in angle. Okay? Now, d is this distance between the two lines. And you can make diffraction gratings. This is in units of micrometers here. And you can make diffraction gratings that are, you know, half a micron apart. That's like 500 nanometers apart, right? So this technology was first developed actually in the late 1800s. I forget the name of the guy who first developed the ability to mechanically etch tiny, tiny, tiny little lines into the surface of a metal. And that would be a reflection grating. So you bounce the light off the grating. Exactly the same analysis works that if you have the light incident straight down, d sine theta equals n lambda gives you the direction of maxima for reflected light from a grating like that. Once this technology was developed, it was possible to do spectroscopy on a really fine scale combining photography and diffraction gratings, and allowed scientists to start studying the spectra of light coming from the sun, coming from, in fact, gas discharge tubes like hydrogen or helium. We'll have those in our classroom here in a few weeks. And what they discovered, of course, with pure gases glowing under a discharge, an electrical discharge across the ends of the tube, is that the light coming out of those things has discrete frequencies. Now, how does that work? Well, you can see the frequencies because they give you what we now call spectral lines. And when you have a diffraction grating, there's a certain line that's formed on a photographic plate that you use to record the angles of the light that's coming either through the grating or reflected from the surface of the grating. And when we get to our section in this course on quantum mechanics and talk about the hydrogen atom and energy levels, we'll see how how the spectral lines that you can see for the discharge spectra come about. And we'll also actually hand out diffraction gratings to all of you, and you can see the lines, the spectral lines yourself. Now, you've probably seen what you might call accidental diffraction gratings. For example, a CD or a DVD, if you hold it at an angle and look at white light reflected from it, you will see that there's a sort of a rainbow pattern. Now, that results from the fact that when white light is hitting the surface of the CD or DVD, there are very, very fine lines in which the information is recorded on the DVD. In fact, the DVD has a spiral starting from the inside going to the outside, and the lines are very, very close together. And you can see white light diffracted and separated into the colors of the rainbow because different wavelengths diffract at different angles relative to the incoming beam. So that's what you would think of as a accidental diffraction grating. Streaks on a dirty window. Suppose you clean your car window. Sometimes if the last time you swiped with your rag left a bunch of streaks on the window and sun hits it, you might see a sort of a rainbow pattern off those streaks. That's because the light is being diffracted from the streaks, which are all very close to each other. Or if you have a metal which is polished, but it's polished with whatever is polishing it moving in a certain direction, leaving very fine lines on the surface of the metal, that can give you a rainbow pattern too. Sometimes people do that intentionally to make the metal look kind of cool. Or, if you're standing in line at the trucks out there by the silo on a sunny day, the person in front of you, if they have long, straight, dark hair, you might see the sunlight reflected off their hair and it looks like a rainbow, and you go, wow, what kind of color are they putting in their hair? Well, they might not be coloring their hair. It might just be that their hair is acting as a diffraction grating for the sunlight.